So now let us make a transition from this microscopic to a macroscopic description. So if you look at the charge density rho and the current density J, these are the source term, and this is where we make the transition from microscopic to a macroscopic description. So what we do is we consider the following separation between charges. That is, we look at the total rho as arising out of free charges which I put into the system, or the bound charges which form basically my material medium. Absolutely similarly, the J free, which is the current I put in from outside, and J bound. So let's just first focus on the charge densities. Usually one is looking at charge neutral media. So in that situation, what I have is that the total charge in the system is 0, right? So you create these charge separations which might be there inside a medium, and hence talk of a dipole wherein the overall charge neutrality is maintained, yet there is a separation between the positive and negative charges. So imagine that my material medium is made of molecules, and my individual molecule has a dipole moment. The definition of dipole moment is simply the sum over Qi Ri. So you will see that I need to sum over both the possibilities where Qi is the individual charges, right? So this could be Q1, Q2, and R1, R2, location of these two charges. So the dipole moment is essentially given as this sum. Note that for a charge neutral medium, Q is positive and the corresponding Q is negative. These are equal and opposite. This is the dipole moment of individual molecules. When I talk about my bulk system, what I have is polarization, which is a capital P here, which is defined as the dipole moment, right, per unit volume. So this is giving me basically the net dipole moment. Here J is over the whole sample. Here I was over the molecule. Each of those charges in the molecule needs to be added up, whereas J here is over the sample. So what you have is net electric dipole moment in the volume delta V divided by the volume. That is how you talk about polarization. So now let's understand this in a schematic manner. So let me consider a one-dimensional medium, and let me look at a one-dimensional problem. So let us say this is my dimension X, and I am looking at a one-dimensional material medium. So in such a medium where I have P to be a constant, right, I have dipoles. This medium has uniform polarization. It has a value, let's say P naught. And then hits 0 here and so on. So now what you have is dipoles which are aligned within such a system. This is a uniform distribution of dipoles. And so this is a uniform distribution of dipoles that you have. Now if you look at this arrangement carefully, because this is uniform, you will see the following, that within the bulk of the material, right, all the charges, every positive charge is accompanied with a negative charge, and all these charges basically neutralize each other, giving rise to zero charge, zero effective charge, zero net charge within this volume. So the only charges that remain, for example, in this uniform medium, are the ones which lie on the surface, right? So you have a series of negative charges here, and you have a series of positive charges which are not compensated by its neighbor, right? So that is the kind of system that you have. So if you now plot, for example, you will see that on the same along the same axis, I am now plotting dp over dx. dp over dx is 0 until you get here, and here you see that there is a positive slope, right? And again it is a constant. When you come to the second edge, what you see is there's a negative slope. This is the kind of derivative of the polarization that you would get for a finite one-dimensional system, right? And you can clearly see that your charge density rho, which is rho bound, these are all bound charges, is basically negative of dp over dx, right? So in 3 dimension, this is simply negative of the divergence of the macroscopic polarization P. That is how one comes up with the notion of a. So you clearly see that on the left edge, you get negative charge, right, which is negative of minus dp over dx, and on the right edge, again you get a positive charge, which is negative of this quantity, and hence the bound charge is essentially resides on this spatial locations where there is a variation in the dipole moment in the material. So it's 0 across the bulk of this material, whereas it is finite where there are changes. I've just taken a simple example of an abrupt change, but then this is precisely where the bound charges reside. In a similar manner, one can discuss the notion of bound currents. Of course, now I had to invoke something which is 3-dimensional. So again, the bound currents have 2 contributions. So let me first write that down. So the 2 contributions to the bound current is coming, one out of polarization and the other one is out of magnetization. Okay, let's just look at the first quantity. So the polarization one arises out of the fact that I have, remember I had polarization which was defined as sum over I of j, which is over all the charges, Ri Qi, right, where Q is the charge divided by volume. So now if I look at dP over dt, which would be simply Qi times dr over dt Ri sum over I times delta V. So now this quantity, this clearly has the dimensions of current density, and this quantity is what we call as the bound current arising out of polarization. So if you have these dipoles where the dipole moment is varying in time, and this contributes to a bound current arising out of polarization. Now the second aspect is what we need to discuss. So we are looking at the bulk magnetization. It is considered absolutely similarly along the lines of the previous discussion, where I take a macroscopically small volume delta V and look at the sum over all the magnetic dipole moments that I might have in my system. So the notion of a magnetic dipole moment is simply the current I multiplied by the area along which the current is flowing. So what you have is, for example, a current which is going in that direction, and then it encloses an area, and so the direction of this area is simply the unit vector normal to the area element A. So for example, if my area is in X and Y, the current loop is in the X and Y, then my A would be the Z axis for this counterclockwise right hand rule would be along the Z axis. Right. So again, I draw my, just akin to the previous discussion, again what I do is draw my sample, the magnetically active sample. So what I have now is my sample. Now let me call this axis as X, that axis is Y, right? And what I have is uniform dipole moments. The dipole moment is uniform. So what I have is current loops which are encompassing my medium. So you will see that within the bulk of the medium, so you'll see that at any given location, right, the currents are cancelling. One is going to the left and other one is going to the right, and so on. So the only remnant current that survives is this surface current, right, which is in that direction, correct? Because there is no cancellation of this surface current. So the magnetization is clearly along the Z direction. So M is sum over Mi Z in this case. So I can write down this in this form, which is I times delta X delta Y. That gives me the magnetic dipole moment divided by delta V, which is delta X delta Y delta Z. So this turns out to be in the difference form I by delta Z, Zk. So now if you look at the variation of M along Y, so my M is only Mz times Z cap, and I'm looking at the variation of dou Mz by dou Y. You will see that this can written down as I by delta Z delta Y. Clearly this is going to be the definition of current density along the X cap direction. Absolutely similarly, you will see that dou M Z over dou X in the difference form can be identified as I by delta X delta Z, which is same as Jy. So the curl of M can be written down in this fashion, particularly because we have only the Z component. We have basically dou by dou Y of Mz minus dou by dou X of Mz. We get back to our bound current. This is the way to schematically basically understand the origins of these bound currents. So one is arising out of polarization and its variation in time, and the second term is arising out of the curl of the magnetization. So now if you put back these terms in our Maxwell's equations, so I'll just look at the two equations that contain the source, that is my del dot E is rho by epsilon naught. This transforms as del dot E is row free plus row bound, and epsilon naught I take to the other side. So the right hand side is row free minus del dot p, which I can rearrange to get the following form, that it is divergence of epsilon naught E plus the polarization P, which is same as row free, which is what is identified as displacement vector, and this is the macroscopic Gauss's law, where now you have included the notions of bound charges into the polarization of the system. You have defined a new quantity called polarization, and that incorporates the bound charges of the system. Similarly, the second equation, which is our Ampere's law, where del cross B is mu naught J free plus J bound. So this I can rewrite as del cross B. Again, I bring mu naught on this side, and I have J free. And remember, there were two contributions to J bound. One was coming from the polarization itself, the time dependence of it, plus the curl of magnetization in a magnetic material. This is the Maxwell's correction. So I can rewrite this whole equation in the following form. I have del cross, and I collect the curls together, which is B by mu naught minus magnetization, and on the right hand side I have J free plus dou by dou t, which is the time dependence coming from epsilon naught E plus the polarization P, which, by the way, you would quickly recognize is same as the displacement vector, electric displacement vector D. So in effect, I can write down, this is the final form. I introduce another field called the H field. So del cross H is simply J free plus dou D by dou T. So essentially I have introduced two new vectors. One is the electric displacement vector, which is epsilon naught E plus P, and the second vector, which is the H vector, which is simply B by mu naught minus M. Now, an important note, the material medium is coming in here with the polarization P, here with the magnetization M. And this is where we make multiple assumptions about the response of the medium, state all the approximations that we make to simplify and parameterize the medium, and that parameterization process is what I will discuss next. So this relationship between D, the displacement vector, and E, the relationship between B and H, these relationships are called constitutive relationships. So let me first indicate what these relations are. For example, so let's look at the electrical properties. So the polarization is basically, as you know, dipole moment per unit volume. It arises from a electric field that generates a polarization, and this is related by a constant. So this epsilon naught is the vacuum permittivity that we already know, right? Whereas chi here is the electric susceptibility. So you see, given such a, so we make multiple approximations to the nature of this susceptibility, whether it is a scalar number or it's a tensorial quantity. Does it depend on frequency? Does it depend on space? And so on and so forth. So we will talk about those approximations later, but let us see what happens when we propose such a relationship between the electric field and the polarization that is generated due to it. So my D vector can be written as, all that I have done is basically put in the explicit form for P, that equation, and this I can rewrite as epsilon naught times epsilon relative times E, and this is what is also written as D equals epsilon. This epsilon R is known as the relative permittivity. Clearly you can see that chi E, the susceptibility, is a dimensionless quantity. Just a small recall, remember that epsilon naught will have the units. You go back to the Coulomb's law and you can derive this. It becomes Coulomb square per Newton meter square. In a similar manner, now I'll write down the relationships involved in between B and H. Again, what we define is our magnetization is arising because of a H field that is applied, and the magnetic susceptibility is denoted by chi m. So I can rewrite my B as mu naught times H plus m. If I put in the form for m, what I get is mu naught times 1 plus chi m, which is the magnetic susceptibility, times H. So I can again write this relationship as B is simply mu naught times mu relative times H, exactly along the lines as we have written earlier. This mu relative is again called the relative permeability. At optical frequencies, there are no magnetic materials, naturally occurring magnetic materials, and hence mu relative is typically just 1. This notion of susceptibility, both electric and magnetic, this is where the medium or that transition from microscopic to macroscopic is actually happening. The idea that one has invoked such a quantity is precisely that transition, and that came about because we separated out, as you know, between the free charges, the free currents, whereas bound charges and bound currents. So let us now look at the approximations one makes with regard to these numbers. So I will mostly focus myself on dielectric properties, that is the relationship between electric field and polarization. Magnetization, as I told you, is not a quantity of great interest at optical, and let's keep it at that. So the first approximation one makes is essentially stating that the relationship between the polarization and the electric field is linear. That is, if I plot my electric field and polarization, then I would get a relationship which is of that kind. That would mean that if I increase electric field 10 times, the corresponding change in the polarization in whatever units would also be 10 times. This linear relationship is extremely crucial because this is what allows us to also implement the notions of superposition, which becomes very powerful tool for us to implement and utilize this for solving complicated problems. So superposition principle holds because we are in the linear range. Now, of course, if I break this relationship, then the relationship between P and E could be nonlinear. For example, it could be something of this kind, which is right, which is a squarish kind of a relationship between P and E. This would be a nonlinear relationship. So in general, one can actually write down a nonlinear relationship between the P, the polarization, P of P can be written as susceptibility chi1 times E, right? Chi2 times E. Now I have written down the specific symbols which are actually tensor products. These are not merely multiplication. But I'll come to that when I talk about isotropic. So with regard to linear, what one is also claiming is that my susceptibility chi, right? This is independent of the applied electric field. This is important. Only then would you see that the relationship between P and E is linear. So it's just a number, and irrespective of the value of the electric field, this would remain just a quantity. When you talk about the nonlinear response, you will see that one can effectively think of the susceptibility as being dependent on the electric field itself, and these terms become, these higher order terms or nonlinear terms become valid when the strength of the electric field is very large. So with the linear approximation essentially simply limits ourselves to within the first, right? This is precisely what the linear approximation is to the actual response. So now we will get to the second aspect, which is the non-dispersive approximation. So when I say something is non-dispersive, what I mean is that the relationship between P and E is instantaneous. That is, the P of t is generated out of a E of t at the time t. Now, by the way, typically this is not true only because every system has got a finite response time. That is, the P at t depends on all the previous history of the it depends on all the prior stimulus that one has put in. That is from minus infinity to t. If I integrate some kind of a response, let's say chi tilde t minus t prime dt prime, that is, I'm integrating all the prior stimuli, right, all the way from minus infinity to the time t, and this term here is my response function. Okay, this is in time. So it's in physics we call it a propagator. It is also known as a Green's function. So there is a finite response time between the stimulus and the corresponding effect when it is realized. The consequence of assuming this instantaneous response is actually in contrast to this statement. One is making a statement that P of t is actually equal to some chi of t times E of t. And this is a patently incorrect statement, because the real relationship involves this kind of a dependence between the electric field and the polarization generated. So the consequence of this is that if I look at this whole thing in the Fourier domain, so what I get is that my P of omega is the chi of omega times E of omega, right? This is the relationship that we truly have. You would see that these two quantities are simply the Fourier pairs of each other. So this would be between convolution in time is what is represented in the top equation, and what it is simply a product in frequency, right? This is the relationship between convolution and products. Frequency dependence of the material, and every material is frequency dependent. One of the most dramatic examples is that of water. So if you look at water, so you know that the refractive index of water, right, N for water, is a well-known number, let's say 1.33 at optical frequencies, right, at let's say 600 nanometers. Whereas if you look at the susceptibility of water, chi of water, that number is close to 81, because that susceptibility, which is typically mentioned, is at DC frequencies. We will see soon that my refractive index is actually square root of 1 plus chi. Actually, specifically, it is a refractive index is mu relative times epsilon relative, and optical frequencies, I told you mu relative is 1, so it effectively comes down to be something like this. So you can clearly see that refractive index of water 1.33 is certainly not the square root of 81. Close to 10 to the power of 14 hertz versus something close to DC, there is a large difference in the response of the system, and this frequency dependent response is what we say when we say the refractive index for glass is 1.5 or water is 1.3. We are essentially, without specifying it in detail, we are approximating and making the things non-dispersive, which is actually an approximation from reality. In reality, you would find that the response is always frequency dependent. So the third approximation that we make, so by homogeneous, what I mean that my susceptibility chi is actually independent of R, right? So it is simply chi, and this is an approximation. Again, for example, you have even glass. One can have various density of glass in such a way that as the density varies, the optical depth varies. So one can have a susceptibility or related quantity refractive index as a function of space. The fourth very important quantity is that we say that the system is isotropic. By isotropic, what it means is that the relationship between P and E is independent of direction. As you know, these are vectorial quantities. So let's say my E is along X, that would generate a P along X. This would be an isotropic system. But you can have systems in which E along X, Y, or Z might create a polarization only along X, right? So now you see that such a relationship is what is called as anisotropic. So where does anisotropy come into play? So this usually comes into play in systems such as crystals. The crystals that do not have cubic symmetry, right? So what happens is that the relationship between P and E, so my ith component of P, this is written down in a most general manner, is given as epsilon naught, which is just a constant, times now chi ij ej, right? So this is the tensorial relationship between the electric field and the polarization. So let me write down the polarization in its individual components. So let's say Px, Py, and Pz is generated out of, that's my susceptibility, and arising out of Ex, Ey, and Ez, right? And you see that now these numbers could be chi xx, chi xy, chi xz. So you see clearly that rather than now just one number, I need to specify uh, a family of 9 numbers, and of course there are symmetries that decrease this number of components. To specify the material response completely, I will actually have to specify these numbers, and of course there is a certain symmetry and ease that comes into materials, and in that situation one can write down and specify just 3 numbers in general. That is my chi xx, chi yy. This is the principal coordinate system. That is when you are looking at a response, all the non-diagonal terms are 0. When you are looking at a response uh, in the principal coordinate system, which it sort of respects the symmetry of the crystal, in that situation I can always capture this uh, anisotropy in terms of these 3 numbers. So for example, a material like glass, which is amorphous, you indeed have the situation where chi x's and chi yy and chi zz is just a single number, and hence we consider such a material as isotropic. So you'll have gases and liquids and amorphous material. These are all isotropic, whereas you will have a family of crystals where the uh, unit cell is not cubic, and all such crystals can give rise to uh, anisotropic response. One of the nicest is the Nicol prism, where there is a notion of birefringence, which is studied in optics, and that arises because of anisotropy. Right. So the next feature that I want to talk about, right, is this notion of loss. So we make this approximation stating that my susceptibility chi is simply a real number. This is what makes the system lossless. But in reality, chi can be written down as chi real plus I times chi imaginary. Right? In general, it has got a real part and an imaginary part, and this imaginary part actually governs the absorption. We will come to this when we look at a classical model of the atom. You would see that all materials have this kind of separation between the real and imaginary parts. The real part actually dictates something called the refractive index, as we know, okay, or the dispersive part of the response is captured by the real part, which is the refractive index, and the absorption captures essentially the loss. The imaginary part captures the loss in the system or arising out of absorption. Now, again, I should tell you that there's a famous Kramer-Kronig relationship. An important note that there is a relationship between chi r and chi I. They are not really independent of each other, and this arises purely out of causality. Okay, so causality is again a very important principle that needs to be respected for physical phenomena. In all physical phenomena, you will see that the cause always precedes the effect, and this causal connection between the cause and effect is what actually leads to a relationship between the real and the imaginary parts of susceptibility. This Kramer-Kronig relationship between the two tells you that if you give me either of them, chi of I, let's say in omega over the whole spectrum, then I would be able to generate from there the real part of the spectrum. I require this input, and you can go back and forth. Either you give the real part of the susceptibility for all frequencies, and then you can generate the imaginary part, or vice versa. So that is again a very important approximation that we make. So the last thing which I want to mention is basically spatially local relationships. That is, if I am looking at E at a location R, this for me generates P at the location R. That is, my E at another location does not create P, which is separated, spatially separated from it. So this local relationship is what is assumed, and hence this would be spatially non-dispersive, right? This would imply that the response is spatially non-dispersive. So we will not get into this aspect too much. So these are the approximations one makes without explicitly stating them. So as practitioners of optics and these areas, we should be well aware of when somebody states a number, we should be well aware of the context in which such a statement is made. And essentially, this notion of parametrization is where the power of Maxwell's equation lies. And it's very important to understand these parameters in their true sense in terms of the underlying approximations one does to arrive at these parameters or numbers. So that is a very, very important part of Maxwell's equations, and also this is precisely what makes it applicable in such wide context. Just at the end of it, I want to quickly talk about the boundary conditions that one has in these systems. So let me just do that, and then we will come to a close for this particular introduction to Maxwell's equations. So the boundary conditions that one talks about are basically these relate to the electric and magnetic fields between two material medium. So for example, this is my boundary, and here I have on the left I have a material which is characterized by permittivity epsilon 1, permeability mu 1. On the right hand side I have epsilon 2 and mu 2, right? So what one is asking is, given such a interface, what is the relationship between the electric and magnetic fields at the boundary of these two media? So I will write down and I'll quickly derive this. I'm sure you are familiar with this. So the first equation is del dot D equals rho free. So let me consider a volume of this kind. This volume has a finite area A, and this cylinder, which encompasses both the media, has a height h, right? And I'm considering the integral form in such a thing. So you see that I will get d dot dA over this closed surface, which is going to be the volume integral rho f dV that might be there. So in case I'm looking at a charge-free region, there are no free charges. That's if at all there is only bound charges. Then you see that my right hand side becomes 0, and if I take the limit that my h tends to 0, right? In that case, you will see that my integral, that is my d1 minus d2, the minus sign is arising because I have my dA has changed its direction. This becomes 0, which simply implies that my d1 perpendicular equals to d2 perpendicular. In other words, epsilon 1 E1 perpendicular equals to epsilon 2 E2 perpendicular. Remember that if there is a finite surface charge, sigma being my surface charge, right? It is not a volume charge, a surface charge. In case there is a finite surface charge, then I can quickly write this out as d1 perpendicular minus d2 perpendicular, if any, the jump arises out of the surface charge. So sigma here refers to the surface charge density, right? So this is essentially my first boundary condition that relates the components of the electric field perpendicular to the interface. Absolutely similarly, I can look at the second equation, which is my del dot B is 0, and this again implies the fact the same argument holds good. Again, I take the limit of h tends to 0, and in this case what it implies is that my B1 perpendicular be equal to B2 perpendicular, and this is my second boundary condition related to the perpendicular components of the B fields. Now I look at my third boundary condition, which has got to do with del cross E is minus dou B by dou T. In this case, again I consider epsilon 1 mu 1, epsilon 2 mu 2, right? These are the parameters qualifying the two media 1 and 2. And now what I do is look at a loop this kind. This loop has got a length L and it has got a height which is h. Again I am looking at the limit that h tends to 0, right? In that case you see that I can write down my del cross E as E dot dl, and because as I take the limit h tends to 0 turns into a loop with an infinitesimal area enclosing it, so my right hand side is invariably equal to 0, because remember that our B fields are smoothly varying analytic functions, and hence the B dot dA will actually, irrespective of the nature of B, as the area decreases to 0, the B dot dA can give me essentially 0. So you see that my E dot dl effectively turns out that my E1 parallel, that is the electric field which is parallel to the length L, is equal to electric field parallel in the second medium. So these are the electric fields which are parallel to the interface, right? And this forms third boundary condition. And the fourth boundary condition in a similar manner arises from the Ampere's law. My del cross H is J free plus dou D by dou T. Again you will see that if I do not have surface currents, then what I would get, this would imply that my H1 parallel is equal to H2 parallel. However, in presence of surface currents, right, this quantity changes, and in general what I get is that my H1 parallel minus H2 parallel is actually given by K surface, which is the surface current, which these surface currents, if any, are confined to the surface alone, right? That is something that you need to keep in mind, and this becomes my fourth boundary condition. So these are my four boundary conditions which I will basically use. So in summary, what I have is that in case I have a interface and I am looking at charge free and current free regions, then my E parallel is continuous, my H parallel is again continuous across the medium, that is in absence of the surface currents, whereas my D perpendicular is continuous. This is my D vector. Interface is continuous. So this is effectively, the four boundary conditions that I have captured. All these things I am writing down in absence of surface charges and the surface current density.